considering push down automaton. So, we consider one example WCWR, where W belongs to 0 1 star. For this we constructed a push down automaton, we wrote down the mapping and so on, right. And in push down automaton there are two ways of acceptance, one is acceptance by empty store, another is acceptance by final state. And by definition the push down automaton is non-deterministic in nature. Non-deterministic push down automata, they are equivalent to context free grammars, that is what we are going to study. So, when you just say final state automata, generally you mean deterministic final state automata, because non-deterministic final state automata and deterministic final state automata are equivalent. Whereas, in the case of push down automata, when you say push down automata, you mean non-deterministic push down automata. Deterministic push down automata and non-deterministic push down automata are not equivalent. Deterministic automata accept only a subclass, which is important from parsing point of view. Okay. So, instead of considering this language, let us consider WWR, where W belongs to 0 1 star, that C is not there. In the earlier case, if you remember what we did in the last class, when you are reading W, when you see a 0 you are putting a blue plate, and when you see a 1 you are putting a green plate, or in the stack you are adding a symbol B when you see a 0 and adding a G when you see a 1. And then when you see a C, you change the state from Q1 to Q2, and when you in state Q2, when you see a blue and a 0 combination, you remove the blue symbol. When you see a G and a 1 combination, you remove the G symbol. Like that you are doing, and in the end the bottommost stack symbol, red symbol was removed, R was removed. What will happen when you have 0 1 star? Suppose you have a string of this form or a string of this form, WWR. In that case, if you want to simulate the same move, after reading this one, when you read the second one, it may be the continuation of W or the beginning of WR, you do not know, right. When you read this one, you do not know whether it is the continuation of W or the beginning of WR. And then suppose you take it as W, at this point again you do not know when you see this 0 whether it is the continuation of W or the beginning of WR, that is not known. So, you have to allow for both possibilities. So, you must have a non-deterministic machine. So, the same thing if you try to do the same concept of acceptance as for WCWR, if you write the machine, it will have two states Q1 and Q2. Input symbols are no C now 0 1, push down symbols are red, blue, green, again you can have the same symbols, and delta is the mapping which you have to define. Then the other components, initial push down symbol is red, acceptance by empty store empty, initial state is Q1, all these components you know. Now we have to write the delta mappings. So, what happens? Delta of Q1 R, when you see a 0, right, you add a blue plate or blue symbol is added. In Q1 when you see a 1 with R as the symbol, you again add a G. So, Q1 GR. In Q1, the top place is blue, right. If you see a 0, that means the last symbol you are read is 0, the next symbol you are going to see is a 0. So, that accounts for two possibilities. It may be the continuation of W or the beginning of W r. So, here actually I should write a flower parenthesis here because it is non-deterministic. Here you can either add a blue plate and stay in Q1, or you can go to Q2 and remove the blue plate. This accounts for the case when it is a continuation of W, and this accounts for the case when it is the beginning of WR. But in Q1, if you see a 1 with B on the top, last symbol red is B is on the top, means what is the last symbol red? 0 in Q1. And when you add a 1, when you see a 1, you can add a green plate. So, Q1 G B. In Q1, if you have a G and a 0, in Q1 you are adding symbols and in Q2 you are removing them, right. In Q1 if you have a G, means last symbol red is 1, you are going to read a 0. So, you will add the blue symbol, corresponding to 0 you are adding B, corresponding to 1 you are adding G. So, that will be Q1 BG. But in Q1 the top symbol is G and you see a 1, that means the last symbol you have read is G and next symbol you are going to see is also, and last symbol you have seen is a 1, the next symbol you have seen you are going to see is also a 1, is not it. So, the next one may be the continuation of W or the beginning of W r. So, both possibilities you must consider. So, you could have Q1 GG or Q2 epsilon. Both possibilities you have to consider. Then in Q2, if you have a 0 and a B combination, you remove that, and in Q2 if you have a 1 and a G combination, you remove that. In Q2 if you get a red symbol, without waiting for input you remove it. Q2 epsilon r is Q2 epsilon, right. This is very similar to what you have written in the last class, but in two of the cases you are allowing for two possibilities, right. Now, let us see how it works on an input 110011. So, consider the input 110011, this is the input, it has to be accepted, right. When it accepts, the push down store has to be emptied, right. We are considering acceptance by empty store now. Acceptance by final state is also allowed and we will show the equivalence. Generally push down automata you consider acceptance by empty store. The equivalence to context free grammar is shown very easily using acceptance by empty store. Now, what is the initial ID? Q1 is the initial state and you are having R as the initial push down symbol. Now, when you read a 1, what happens? Q1, this 1 has been read, next ID will be, this is the portion to be read and you are going to add a G. Right. Now, in Q1 you are going to read a 1 and the top symbol is G, Q1 1 G, Q1 1G, there are two possibilities. Either you stay in Q1 and add a green symbol, or you go to Q2 and remove the green symbol, right. So, there are two possibilities. One is Q1, 1 has been read, this is the portion remaining, and you can add a G symbol. The other possibility is you go to Q2, read a 1, but then this is remaining, remove the G symbol, so you get R. When you get a Q2 and R combination, when you are in state Q2 and see a R symbol, without looking into the input, you remove the R symbol. So, this will go to Q2 0011 epsilon. Now, once the stack is emptied, further move is not possible. See, if any move has to take place, then there should be at least one symbol on the push down store. Only if there is at least one push down symbol, a move can be defined. If there are no symbols, it cannot be defined. So, in this case you cannot proceed further, but at the same time the whole of the input has not been read. The string is accepted if and only if the whole input is read. If you stop in the middle, it has to be rejected, right. So, continuing in this, you are having a G and a 0. When you see a 0, you have to add a blue symbol. So, Q1 0 has been read, this is a portion remaining, you are adding a blue symbol on the stack. Please note that we are following the convention that the leftmost symbol is the top of the stack. Now, in Q1 you are seeing a 0 and the top plate is a blue, or top symbol is B. There are again two possibilities, it can be the continuation of W or the beginning of WR. So, you can remain in Q1, read the 0, add a blue symbol, this is possible. Or you can go to Q2, B has to be removed, 0 and a B combination, you remove the blue symbol. So, portion of which is remaining is 1 1, on the input you have to still read 1 1 and you have GG R. Once you go to Q2, if there is a 0 B combination, you remove the B, 1 G combination, you remove the G. If there is another combination 1 B or 0 G, you have to halt. Now, here you find that you have a 1 G combination, remove it, again 1 G combination, remove it, and in Q2 when you have a R on the top, without looking for the input you can remove it. So, you go to Q2 epsilon and this is the accepting configuration. This is the accepting configuration for empty store, right. Now, in this case what happens? When you have a 1 and a B, you have to add G. So, next thing will be Q1 1, Q1 1, G B B, G G R. Now, you are in Q1 and you are getting a 1 and top symbol is G. So, again it is can be the beginning of WR or the continuation of W. So, one possibility is you go to Q1, read the symbol, add 1 G, another thing is you go to Q2, this has been read, and you will remove the G for 1. So, you end up with BB GG R. You cannot proceed further here because in Q2 and B no symbol is there. You have read the whole input in this case, but the stack has not been emptied. Push down store still contains something. So, this is not accepting configuration. Here you are again you are in state q1, whole input has been read, but something is there on the stack. So, this is also not an accepting configuration. The accepting configuration is this, right. So, how do you go to the accepting configuration? Make this move, this move, this. There may be several possibilities, okay. That is why it is non-deterministic, out of which if one sequence takes you to an accepting ID, accepting configuration, the string will be accepted. The string will not be accepted if there are no sequence of moves which leads you to an accepting ID, okay. None of it is accepting, then only the string will be rejected. Here one sequence leads you to an accepting ID, other sequences may lead you to non-accepting IDs, does not matter. If there is at least one sequence which takes you to an accepting ID, the string will be accepted, otherwise it will not be accepted, okay. So, this is the difference between deterministic automata and deterministic PDA and non-deterministic PDA. The definition of deterministic PDA is like this: a PDA, M is equal to K sigma gamma delta Q naught Z naught F. If it is acceptance by empty store, it is empty, is said to be deterministic there are two conditions. If for all q in k and z in gamma, if delta of q epsilon z is non-empty, then delta of q a z is empty for all a in sigma. What does that mean? This is the first condition. I will write down the second condition also, then we will see what it is. If for no q in k, a in sigma union epsilon, z in gamma, does delta of q a z contain more than one element. What does that mean? The second is easy, the next choice is unique, that is what it means. In deterministic case, the next choice will be unique, right. What does the first one mean? For all q in k and z in gamma, if delta of q epsilon z is non-empty, then delta of q a z is empty for all a in sigma. That means that for a particular state and a push down symbol combination, q z combination, either you use epsilon move, when you do not read any input symbol, that is called an epsilon move, right. Either you use an epsilon move or you use a true input move, you read a symbol. For a particular q and z combination, both you do not allow for a deterministic push down automata. Look at this one, This is because of this it is non-deterministic, but here you see in the earlier example of WCWR also we had this move. When you are getting a Q2 and R combination, when you are in state Q2 and the top symbol is R, then you remove it. When you are in state Q2 and R, no move is defined for A or B, I mean 0 or 1, right. So, for this combination Q2 R combination only epsilon move is allowed. Okay. Similarly, for some Q and Z combination, if you allow for epsilon move, you do not allow for true input move. You call them as, generally you call them as epsilon move, true input move. For a deterministic push down automata, for a particular state and a push down symbol combination, either you allow for epsilon move or you allow for true input move, both you do not allow. That is the first condition. The second condition is, when you say delta of Q A Z is P gamma or something like that, that is unique. At most you can have only one possibility. It is not necessary that you should define for each and every combination. Like in the finite state automaton, you draw the state table, everything you fill, and whenever there is no possibility you put a dead state. See, you make the move, machine move, go to a dead state, and once it goes to the dead state it remains there. Here we do not specify like that. Sometimes delta QAZ need not be specified at all, but whenever you specify that, either A can be epsilon or a true input, whenever you specify it, it has got only one ordered pair, P gamma. You cannot have P1 gamma 1, P2 gamma 2 like that. So, in the first example when we consider for WCWR, we never had two possibilities, only one possibility was there. Here in this one there are two possibilities, that is why it is non-deterministic. Here the first condition is not violated, but the second condition is violated. You have two choices here. Okay. In some cases, when you allow for both a true input to be read or an epsilon to be read for the same push down symbol and the state combination, it becomes non-deterministic. So, non-deterministic push down automata are equivalent to you do not say NPDA, you say generally PDA. PDA means non-deterministic. This is equivalent to CFT, and DPDA form a subclass. It is contained in. So, if you draw the class like this, regular sets will be like this. CFL includes regular set, context free languages. This is the family of deterministic context free languages. What is DCFL? Languages accepted by deterministic push down automata, they form a subclass. One example is this WWR. Inherently ambiguous context free languages cannot be accepted by DPDA. You have to have non-determinism there and so on. What is the grammar corresponding to this? This is finite state automata. This is PDA corresponds to context free grammar. For deterministic push down automata, the corresponding grammars LR grammars. These are very useful in compilers. You have LR 1 parsing table, LR 2 parsing table and so on. And there is an automatic parser generator called YAC. Given a grammar, it will try to generate the parser automatically. Okay. So, those concepts are used. If there is enough time, we will consider in detail about LR0 tables, parsing tables, how do we construct the parse tables and so on. Depending upon the time we have, we will have that. The next thing we have to consider is the equivalence of acceptance by empty store and acceptance by final state. Equivalence of acceptance by empty store and acceptance by so we have a result. L is a context free language. L is equal to T of M2 for a PDA M2. T of M2 means acceptance by final state. We use the symbol N for acceptance by empty store. If and only if L is equal to N of M1 for some PDA for a PDA M1. This is the result we want to prove. That is, if there is a language which is accepted by a push-down automata by final state, then there is another push-down automata which will accept the same language by empty store and vice versa, right. So, the first part of the proof is L is equal to T of M2 then you have to construct M1 such that L is equal to N of M1. Given M2 you have to construct M1. Now, how do you do this? M2 is say K sigma gamma delta Q naught Z naught F, and M2 accepts L by final state, set of final states are given by F. Now, you construct M1, you add two more states to this Q naught dash and QE. What does Q naught dash mean? I mean, this is a new state. QE means erasing state. We wanted to have it as erasing state, that is why we call it as QE. Same sigma gamma union a new push down symbol X naught, which is not already there in gamma. Add a new push down symbol and mapping is delta dash, or if you want to have call this as delta 2, call this as delta 1, that is more easy. The new state which we have added Q naught dash is the initial state here, and the new push down symbol which we have added is the initial push down symbol, and because it is acceptance by empty store, you need not have to write the final states. So, what we do is we want to construct M1 which will accept the same language by empty store, and for that what we do is to the set of states you add two more states Q naught dash and QE, and this Q naught dash is the new initial state. The symbol which you have added, new push down symbol you add to gamma, and that is the initial push down symbol, and so on. Now, we have to define delta 1. How do you define delta 1? delta 1 q naught dash epsilon x naught contains q naught z naught x naught. The first move is like this, right. Then delta 1 q a z, whatever you have, I mean whatever delta 2 is equal to whatever mapping you have there, you have here also, includes this. Whatever mappings are there in delta 2, all those are in delta 1 also. Then if q belongs to f, you have a final state, then you have delta 1 q epsilon z is equal to q e epsilon, where z belongs to gamma. Gamma union x naught, x naught also. 4 delta 1 q e epsilon z. I should not write equal to, because rather contains is the proper word. Contains q e epsilon for all z in gamma union x naught. Now, how M1 simulates M2? Let us see how M1 simulates M2. How will M2 accept a string? You have input, you have a push down store initially. Initially it will be in q naught and have z naught on the stack, and when it accepts this, it goes to a final state qf, some final state, something may be there on the stack. That is how this input is accepted by M2. M2 accepts in this manner. What does M1 do? M1 has to accept the same string. So, this one if you write in the formal ID way, q naught, say some w is accepted, this is w, say w z naught in M2. This M2 means in the move is in M2, you go to some q, to denote it as a final state I will write as qf, qf epsilon some gamma, right. Now, what does M1 do here? M1, it starts with this w and the initial state q naught dash and with x naught as the bottommost push down symbol. This is the situation with which it starts. The first move says that delta 1 q naught dash epsilon x naught contains q naught z naught x naught. So, without reading any input symbol, epsilon move, without reading anything, the state changes to, it changes to q naught, from q naught dash it changes to q naught and it writes a z naught on top of x naught. Now, you have almost come to this situation, is not it, except that there is a x naught below the z naught, it is exactly similar to this. Then M1 will simulate the behavior of M2, it will behave just like M2, that is what is given by delta 1 QAZ includes delta 2 QAZ. So, it will have all the moves. So, it will read the entire thing, and at the end what happens? It goes to a final state QF, right, and stack, in this case it had a string gamma, here it will have gamma, below that x naught, right. Now, afterwards, once you reach a final state and the whole input has been read, what it is going to do is, the third move says that you go to the erasing state. So, from QF it will go to the erasing state and start erasing one by one all these symbols. It will erase all the symbols. So, you get acceptance by empty store. If you write in this way, starting from Q naught dash W x naught, M1 will make one move, it will go to Q naught, it is an epsilon move. So, no input has been read, Z naught x naught, then by making more moves it will go to some QF, whole input will be read. This portion is exactly similar to this gamma, but below that you have the x naught, and afterwards it starts erasing and you get QE epsilon. So, if a string is accepted by M2, it will be accepted by M1. If it is accepted by M1, it should be accepted by M2. How is that possible? See, look at this, the only move where the start state is used is this. So, you have to start with this, and once you go to the erasing state, it is only epsilon, you cannot read any input, you have to keep on erasing, that is all. Once you go to QE, the whole stack has to be erased, you cannot do anything else, right. So, you have to use this in the end, you have to use this in the beginning, and in between you have to do this. That is the only way you can proceed. So, in between when you do this, you are simulating M2, is not it? So, if it is accepted by M1, that means the first move you make like this, and the end you erase the stack symbols. So, in between you would have gone from this to this, right. That means it is accepted by M2. So, the language accepted by M1 and M2 are the same. M2 is accepting it by final state, M1 is accepting by empty store. Okay. Now, the second part of it, given M2 to construct M1. Okay. So, M1 is given as K sigma delta K sigma gamma delta 1 Q naught Z naught phi, right. Its acceptance by empty store, it is given like this. So, M2, to get M2, what you do is, to the set of states you add two more states, Q naught and QF, Q naught dash and QF, two more states you add, sigma is the same, you add one more push down symbol x naught, and the mapping is given by delta 2. The new state Q naught dash is the initial state, x naught is the initial push down symbol, and the only final state is QF. So, as in the earlier case, we add two states, Q naught dash which will act as the new initial state, QF which will act as the only final state, and new push down symbol, you add one more which will act as the initial push down symbol, and the only final state is QF. The mapping we have to write now, delta to Q naught dash epsilon x naught contains Q naught Z naught x naught. As in the earlier case, you can understand that this move is from the initial ID of M1 you go to the initial ID of M2, you go to the initial ID of M1. That is why this mapping is written. Second, delta 2 QAZ includes delta 1 QAZ for all Q, for all A, for Z, etc. Whatever mapping is there in M1, all those mappings are there in M2 also, right. Then delta 2 Q epsilon x naught contains QF x naught. For all Q. Again the idea is similar. How does M1 accept a string W? You have a string W. How is this accepted by M1? Start with Q naught with Z naught on the stack. After reading this, you go to some state Q and the stack is emptied, right. Now, how will M2 accept the same W? You have W, you are in the initial state Q naught dash and you are having x naught, right. You first move says Q naught dash epsilon x naught contains Q naught Z naught x naught. So, make one epsilon move, that is do not read any symbol. From Q naught you go to Q naught dash, you go to Q naught and write Z naught over the stack. Now, you have come to the initial configuration of M1, simulate M1. At the end you go to some state Q and the stack is emptied, but the bottommost symbol x naught remains. Its stack is emptied up to Z naught. You are marking the stack with x naught now. So, x naught will remain. So, finally, when you end up with just x naught on the stack, that means the whole stack has been emptied in the case of M1. So, you make one more move, go to the state QF. This is what it means. When you just have x naught alone on the stack, from any state you go to the final state, right. So, in this way you can simulate the behavior of M1 by M2. The languages accepted are the same. So, if a string is accepted by M1, it will be accepted by M2, and if a string is, that you can very easily see, if a string is accepted by M2, the way you proceed is first you have to go to the initial this move can be used only in the beginning and this move can be used only in the end. Once you go to QF, there is no move defined for QF. After, once you go to QF, you halt, you stop, right. There is no move with delta QF, etc. So, you have to use this move in the beginning and you have to use this move in the end. In between you have to use the other moves. So, that means from here to here, first you have to use, then you have to use this, then you have to use this. That means when you use this, you are really simulating M1. So, if a string is accepted by M2, it is accepted by making this move, then some moves here, and then this move. That means it makes all these moves, so it will be accepted by M1. So, if a string is accepted by M1, it is accepted by M2 and vice versa. So, they are same. Okay. So, acceptance by final state and acceptance by empty store are equivalent. But please remember that for the same machine it is not like that. See, you may define a push down automaton by final state. Then in between it may, for reading, when it reads a string, it may empty the stack. So, that string is not accepted by the machine. Okay. It is not true that n of m is equal to L of m, T of m for same machine, right. If some language L is accepted by one push down automaton M1 by empty store, it can be accepted by another push down automaton by final state and so on. But for the same push down automata, supposing you define a final state, then acceptance by empty store and final state need not be the same, they will be different. Usually when you define acceptance by empty store, you do not specify any final state, you say phi, right. And the way why we are having this x naught in the beginning, when we want to construct M1 from M2, we are having a new push down symbol. If you do not have that push down symbol, what may happen is, while trying to simulate, it may empty the stack and accept something else which you do not want to accept. Such a thing may happen, right. So, this is about equivalence between empty store and final state. Usually we take only acceptance by empty store in the case of push down automata. That is very convenient actually for proving results and all, for especially for proving the result with context free grammars, equivalence with context free grammars. It is very convenient to take acceptance by empty store. And there are so many results about making the push down store. You have a push down store. This push down store can grow, come back and so on. When it grows and comes back, it is called one turn. So, how many turns does it make? Such things, even today there are papers coming on such things, turn bounded push down automata, when it, how many turn it makes and so on. If it makes just one turn, it will accept what are known as linear languages. What are linear languages? A power n, b power n, WWR, WCWR. The just stack grows and comes back, right. If it just makes one turn, the language accepted will be a linear language. So, even today research papers are being published on this turn push down automata, how many turns, and when it comes back, should it erase the bottommost symbol or just keep the symbol or go to the initial state and things like that. Okay. So, next we will consider the equivalence of with the grammars in the next class.